For today, we have the pleasure and honor to have Dr. Michael Watson with us. Or as within the family of INCOSE, we call him Mike. So Mike has 34 years of experience within NASA. He just recently retired, but within NASA he has worked with lots of different space systems, but practically, but also had led a number of efforts within NASA to look at the discipline as a whole and the systems engineering approaches, and have led a number of efforts to compile it into technical publications such as the Engineering Elegant Systems, Theory of Systems Engineering, and Engineering Elegant Systems, the Practice of Systems Engineering. He has also shared within INCOSE, the Complex System Working Group, and led the revision of the Complexity Primer for Systems Engineers, something that you can download as a member. But also recently, what we will talk about today, he led the effort within the action team that has produced what we'll hear about now, the Systems Engineering Principles. So Mike, will you take it from here? I understood that your video is not working, but your voice should be there and your presentation.
Yes.
If I stop share now, maybe you can take it over.
All right. Good after middag. It's good morning here, but it's good to be here with you to talk about systems engineering principles today. Let me get this in presentation mode. As Tom said, I've just recently retired from NASA and am now working with the Dynetics company, working on human landing systems, so building a lander for the moon. Over the last several years, been doing a lot of work on systems engineering research. And Tom mentioned the work that I led with the NASA Systems Engineering Research Consortium that led to a set of systems engineering principles that kind of help us define systems engineering, kind of help us understand some of the basics that we need to do, particularly when we're applying the processes and some important elements of that. With the NASA work being completed about 2018, I approached INCOSE leadership about taking it and maturing it and working with that a little bit. We had defined 7 postulates, 12 principles, 4 hypotheses, and had matured that with discussions in 17 universities in the United States and 1 in Norway, with 5 companies, 4 NASA centers, and the Air Force Research Lab. Looked at how a lot of companies apply systems engineering processes across multiple industries, and presented kind of the initial results from NASA at the INCOSE IW 2018. And so we spent the next year forming an INCOSE action team that started meeting in March of 2018. And we had a face-to-face in Washington, D.C. Of the membership in December of that year. They kind of crystallized the principles that from an INCOSE standpoint and helped to mature them a little bit further. We reviewed over that course of the year 2018 a lot of current literature, all that we could find on systems principles and systems engineering principles. We developed some criteria for what would be INCOSE systems engineering principles, and we published that in an Insight magazine article in May 2019 as part of the Future of Systems Engineering theme, which you can get access to that. If you're an INCOSE member, you should have free access to that. And in that work, we laid out 15 systems engineering principles, 3 systems engineering hypotheses. And the result of some of that work is we also published a survey article in the CBOK, the Systems Engineering Body of Knowledge. And I have the link here, and I'll send these charts to Tom so that you can have those or have these. But I have the link here that you can that you can access the CBOK article, which is a survey of what we did, but also the other articles that we looked at. And so that's really good. One of the things that we were trying to do, really starting with NASA and looking at systems engineering principles, was trying to find the underlying basis for systems engineering. If you go to other engineering disciplines, they have their characteristic equations, their basis of what they're doing, why they do, how they approach their engineering. And so the question we had was, what is that for systems engineering? We have processes, and so do all other engineering disciplines. They have an approach, a method, a way, a process to execute their work. But what's the basis that sits underneath that, right? And so we were looking for that. The consortium came up with some postulates, principles, and hypotheses. And the reason we did that was going back and looking at the history of science and engineering, and realized that Ludwig von Boltzmann had put together initially a set of postulates for the gas dynamics laws back in the late 1800s. And when we looked at that approach, what he did, how he did it, gas laws, billions of molecules in a container, what's the distribution? It seemed to us to represent a fairly complex arrangement, complex system. And so how did he go about defining those laws? And he started with postulates, so that we ask ourselves, what are the postulates of systems engineering? And we came up with 7 of those. Then we expanded those into 12 supporting principles that were really just expansions of the postulates. And we had a few items that needed proofs before we could say that they were correct or not. And those became hypotheses. In 2018, as we looked at that within INCOSE, we said, well, really the principles and the postulates, they might be a little bit duplicate. Let's go with principles and just expand those out. And when we did that, we came up with 15 principles. Just a little bit of moving some of the ideas and concepts around within the principle space. We also promoted one hypothesis. We were able to conduct a mathematical proof, and you'll see principle 5 that I'll show you this morning or this afternoon, that started as a hypothesis. We ran the proof, and now we have that as a principle. So this is some fairly successful activity in how we developed this. Now, if I go to the next chart here. There we go. The members of the team included David Rousseau over in the United Kingdom, Brian Messmer, Gary Rodler, Chuck Keating, Bill Miller, Javier Cabello-Modio, Scott Lucero, Rob Gold, Eileen Sedmak, Cheryl Jones, David Long, R.W. Russell, and Robert Dillow were the main contributors to the INCOSE team. And it was a really good, broad team. Gary Rodler brought a lot of energy and excitement to it. David Long was instrumental in getting the action team set up within INCOSE. David's who I approached first about, hey, what do we do with these? Could INCOSE benefit from this? Chuck Keating brings a lot of work in the governance of complex systems. Brian Messmer brings a lot of work on system value modeling. David Rousseau brought a lot of systems philosophy work in and really helped us with terminology and language and how we needed to define things. Bill Miller contributed, and everybody knows Bill within INCOSE. Javier was really good from Oregon State. He's also the chair of the System Sciences Working Group. So Javier and David kind of brought that connection in, which helped with that. And then we had some others from various U.S. organizations that were just interested in participating, and brought some perspectives in that were a little different from what we had at NASA. So that was good to have. So that was the membership of the action team. Kind of the first thing, and Gary Rodler was really good about leading this, was what constitutes a principle? How do we understand principles, right? And so we were looking at that, we realized a principle transcends life cycle. So a principle is not applicable to a specific phase of the system life cycle. It transcends all the phases. It's applicable in all the phases of the life cycle. It transcends all types of systems, whether we're talking ships or aircraft or rockets or electrical power plants or desalination systems, water systems, whatever we're talking about, the principles, if they are a principle, should transcend all types of systems. And then it should transcend the context meaning it's applicable whether you have a large amount of money to fund the project or a small amount of money to fund the project, whether you have 10 years to build the system or 10 months to build the system. It should transcend its context. That also includes the international culture and the differences within each of the countries, the laws and the regulations. The principles should apply regardless of that legal context, policy and law context that you find out there. And so we looked at that. The principle should inform a worldview of systems engineering, not be a how-to, but again, informing that worldview. Should be either supported by literature or widely accepted in profession, or both. And should be, when we were looking at the writing, we wanted to make sure that they were focused, concise, and clear. And so that was what we looked at within INCOSE to kind of refine and develop the final list of principles that we put out in the document. One of the things we looked at real early on is what is the relationship between systems engineering principles and system principles? And what we found is a lot of people talk about principles, but they're really talking about system principles. And so we looked at that and realized they're actually different. Systems engineering principles are principles which guide the engineering of the system. How do we conduct the engineering? It gets back to processes, but also what are the underlying foundations of that? How do we look at that? System principles are principles which define the characteristics of a physical or a logical system. So they are system related, where systems engineering is the approach relationship. And then there's also a set of organizational principles which define the structure and functioning of an organization. And that gets us into the sociological aspects of the principles. And so we recognize that some of these organizational principles do, in fact, impact systems engineering. We need to be aware of the organizational context in which we are working. If you look at automotive industry, right, there's been some look at the differences that car manufacturers produce. They can have the same basic goals of producing a car, and yet when you look at the final product, it's very different. And where is that coming from? It's coming from the organizational side and what people value within that organization and how that manifests itself into the design. And so that's an important aspect that as systems engineers, we need to be aware of because what works well in the application of the processes is going to be very dependent on what our organizational values are in systems engineering. The principles encompass the basic system principles of the specific system being engineered. So the physics, the logic, all of those types of aspects. You can't be a systems engineer in a rocket if you don't understand how a rocket is engineered. And so you have to get into the physics a little bit, the orbital mechanics, those types of things, thermodynamics. You do have to understand those and how they're applied. And we looked at different system types in NASA and realized that most system types that we engineer today are thermodynamic. There are some structural system types, buildings and bridges, but a lot of the systems that we build are thermodynamic. They're systems that are dynamic in motion in some sense. And so that's kind of an interesting understanding. But there are other types, communication systems, data systems. There are other types of systems that are not governed by the thermodynamics. Sociological aspects are really important, and I've already mentioned that. And so we saw the system engineering principles as guiding the application of the systems engineering processes with regards to the type of system that you're engineering, and with regards also to the organization in which you're working. And as I mentioned already, two different companies can come up with different looking solutions for basically the same set of requirements. You can see that in aircraft developments, or you can see that in the automotive industry, as I mentioned. And so that's important to kind of understand, that we need to know how to apply the processes in an effective manner, and the principles help us to understand that. And then system principles address the properties of the systems, which again are important to properly engineer or systems engineer the system. So let me jump into the principles, and I think what I want to do with this is pull up the actual document itself. Let me make sure that I'm still sharing this. Okay, let me make it full screen. Okay, close that up. And so this is the document that you can download from the INCOSE bookstore. If you're an INCOSE member, it's no cost. If you're outside of INCOSE, haven't joined yet, then it's a minimal cost of $15 is what the INCOSE board decided to put on it. But the document itself has a lot of important features in it. We define up front the purpose, the scope. We do have definitions of terminology that we wanted to capture. We give you the background of the work that we did and how the different types of systems engineering principles that we reviewed and where those came from. Gonna give you the background. Some of what I've already discussed here as part of the presentation. We do define the key terms that we use: heuristics, elegance, hypothesis, principle are all defined there. But I want to get down to the principles themselves, right? And so I mentioned already that there are physical and logical principles, and there are sociological principles, and there are some principles that address both. So we've coded those within the principles document. So if you see this particular symbol, where it's talking primarily that the principle is focused on the physical logical system. If you see this particular symbol or icon, then it's addressing the sociological principles. And you'll see some that are addressing both. And you'll see that, and so you'll see those codings throughout the document. What are the principles? I'll just go through these. There's 15, so I'll go through them rather quickly. But I do want to do that in the context of what we have here in the document. So Principle 1, systems engineering and application is specific to stakeholder needs, solution space, resulting system solutions, and context throughout the system lifecycle. So systems engineering, it needs to be specific to the solution set, the stakeholders, and the context that you have throughout the system lifecycle. And that's really, really important. You know, we have a nice graphic here that says, hey, you know, there's all types of systems that we're looking at. Now, one of the things you'll notice with the principles is we do give a description to kind of set an understanding of what the principle is saying. And then we talk about the evidence, right? I talked about the importance of having evidence. So we talk about the evidence of the principle, and then we give the implications for practice. How do I use these in practice? What does this mean to me in executing the systems engineering processes? And so we give you that as well for each principle, which I won't talk through this morning. That would be like a 4-hour talk if I got into all of that. But it's great to read, and it's very readable. We had this peer reviewed by AIAA, IEEE, and NDIA, so 3 sister organizations to INCOSE, had their systems engineering groups look at it, and that really helped with the writing and the formatting, and so you'll find the document to be really easy to read through. Principle 2, systems engineering has a holistic system view that includes the system elements and the interactions amongst themselves, the enabling system, and the system environment. Now, this principle is fundamentally important in and of itself because it contains the mathematical definition of a system. So I was working with the Air Force Research Lab here in the United States, and they were working with a category theorist. I don't know if anyone is familiar with mathematical category theory, but he read the principles and he looked at this one and he said, well, you know, that's the definition of a mathematical category. A category is a construction in math that contains objects and the relationships between the objects. And that's what you see in this definition: system elements, and then the interactions of the system elements. And so that is actually pointing us to a mathematical basis for systems engineering. And so that was very exciting to us to kind of find that. That's what we were trying to do with the original postulates. This was originally a postulate, which we recoded to a principle. That's what we were trying to do with that. And we've seen some early fruit that's helping us go off and then study mathematical category theory. So you'll see a brief description of that here. Principle 3, and you'll note the sociological icon, says that system engineering influences and is influenced by internal, external resource, political, economic, social, technological, environmental, and legal factors. So the PESTLE construct that came out of Oxford University. That's really important. And notice the words, it influences as well as influenced by. So when we're doing systems engineering, we are not only being influenced by the organization structure, the policy and law structure of the nation that we're working in, or if we're doing international nations that we're working in, but we also influence those. We come back and say, hey, national governing authorities, you know, here's something about our system that would be a benefit to you, but this is what it means in the political realm, or this is what it means within your law structure. And you'll find in the United States, I've seen where our Congress will go and say, okay, you know, hey, NASA, we would like for you to do that. We're going to address it so that you can. And so you'll see influence back and forth. That happens within companies as well. As you say, hey, we want to do this, but our policy is to do it differently. how do we address that, right? And so those discussions can happen. So you're going to influence as well as be influenced by the pestle factors. Principle 4, both policy and law must be properly understood to not overly constrain or under constrain the system implementation. That's really important. Here in the United States, in my career at NASA, I'm working with Congress. Sometimes Congress writes laws that are very explicit and well-defined, and you need to follow them as they are written. Sometimes Congress writes laws that are just stating what they would like to see. We call them desires. And when you go back and you ask them, and that's really important that you go back and ask them, when you go back and ask them, hey, you said this, did you really mean this? Because there's another way to approach it. And it will help us to relieve some of the constraints we have on us. And Congress will almost always say, oh yeah, well, yeah, go do what you said, and they'll fix it in a follow-on law later. So we talked a little bit about that with Principle 3. But Principle 4 really focuses down on that policy and law part. Now, policy can be your company's policy as well. And you need to understand what those actually allow you to do and what they really are preventing you from doing, what you can ask for, and what you what is hard defined, so that it's not something that you're going to be able to waiver. And then that influences how you approach your systems engineering for the system within that organization. And so it's really important to understand what policy and law, what the constraints are, not to over constrain yourself, and certainly not to under constrain yourself. Principle 5, I mentioned earlier, we actually did a proof for this. The real system is the perfect representation of the system. And this gets back to modeling. The model isn't always an abstraction. The system model is always an abstraction of the system. The only perfect representation is the system itself. And we actually followed what's called the Kullback-Leibler information model to run that proof. And that's pretty straightforward. But what it says is, hey, when you build your model, your parameters are always abstractions of the total set of parameters. We never have everything fully measured. We never go down to the quantum states of every atom in the system. So we abstract that. That's what we get when we talk about material properties, right? It's an abstraction of really what's happening at the quantum level. And so as we do that, we realize that what we're modeling is a characteristic property of a part of the system rather than the full property. And so the model is always an abstraction. That's very true for SysML and other modeling types. And so we just need to keep that in mind and not get lost in our goal is to build the model. Our goal should be to build the system. And the model helps us understand the system. And so this principle kind of makes that point for us. Principle 6, a focus of systems engineering is a progressively deeper understanding of the interactions, sensitivities, and behaviors of the system, stakeholder needs, and its operational environment. This is really important as you go through the system from requirements definition, the systems engineering process, from the requirements definition to design to test. You're going to get a progressively deeper understanding of everything that's going on with the system. And so it's not unusual to have requirements mature late. And if you write the requirements down early with an incomplete understanding, it's not unusual. It should be expected that they're going to change as you go through and learn more about the system that you're trying to build. So it's important to keep up with that progressive nature and not let that surprise you. Now, this principle has several sub-principles, and I'm just going to kind of read through these. But mission context is defined based on the understanding of the stakeholder needs and constraints. Requirements and models reflect the understanding of the system. I just mentioned that as part of, and you'll see a lot of coupling. This is a good example between the principles. And there should be, right? Because it's a system, it's describing systems engineering. So you'll see a lot of coupling. And we see that as a good thing, because we did look at that very hard to see if we were being redundant or duplicate. And in all cases that are remaining, we said, no, these are not actually duplicate or redundant. So this principle is, or this sub-principle is really important because it gives us what's the purpose of the model. Requirements are specific, agreed to preferences within the developing organization. So requirements are agreements. This gets back a little bit to value modeling and how they view requirements as preferences, as opposed to very exact requirements. If you say the car should be 2,000 kilograms, that's great. But what if with value model, people will come back and say, well, what if it's 2005? Did you miss the requirement? Is the car not work? What does that mean? And so they tend to call them preferences. What we said in looking at that is, you know what? We need to agree to our preferences. We do need to have targets to work towards. We do need the 2,000 kilogram agreement to work towards that and manage towards that. And so it's important to understand how we're using requirements and what they represent. Requirements in system design are progressively elaborated as the development progresses. You can see that. Modeling of systems must account for system interactions and couplings. Talked about that in some other principles as well. System engineering achieves an understanding of all the system functions and interactions in the operational environment. That's really what we're about, is if we're going to engineer the system, does that interact with the operational environment, with the user, the consumer, the customer, the operator, the environment? How does that interact? And then system engineering achieves an understanding of the system's value to the system stakeholders. This points us towards system value modeling, which is a particular modeling type, trying to model mathematically the preferences of the stakeholders. And then understanding of the system degrades during operation if system understanding is not maintained. It's really important to realize that if we don't maintain our system understanding, we will lose that as you go through, particularly if you're looking at a program that lasts for 20 or 30 years, say the space shuttle, which was a 30-year program. If we don't maintain our system understanding from 1978, and we found examples where in the aircraft industry where they didn't maintain it, and when they went to do maintenance upgrades 20 years later, they didn't know why they had written the specification the way they wrote it, and it was driving them to put heavier equipment into the aircraft as an upgrade than they actually needed. They had to go back and re-engineer it. And so they had lost that understanding of the system, and that had slowly degraded during operations. People just forgot why they wrote that down because they were focusing on what was actually happening rather than why that had been done. And that basis is really, really important. So that's an important sub-principle as you progress through the life cycle. You get to principle 7, we get back to a sociological principle. System engineering addresses changing stakeholder needs over the system life cycle. Stakeholders are also progressively understanding what the system's doing. What I saw at NASA was NASA headquarters would look at it and go, hey, this capability, you have this capability, we want to use that now. And it's like, well, that's great, but we weren't starting with that. So now you're adding something to us. And what does that mean? And so you're going to expect, as they understand it better, they are also you're going to see their needs evolve. And so, be prepared to handle that as you go through the systems engineering life cycle. Principle 8 is a good example of a principle that addresses both the physical logical side and the sociological side. System engineering addresses stakeholder needs. taking into consider budget, schedule, and technical leads, along with other expectations and constraints. It gets back to the context that we need to understand not only what the stakeholder is asking for, but what's the budget that they're giving us and what's the schedule. Because that makes a big difference in the system solution that we can provide. And we have to fit into all of that. If I have a year and $1 million, or I have 10 years and $10 billion, they're very different systems, even if the initial requirement may be the same. And so how do you do that? You have to bring all those things together and make sure that the solution set is fitting the full set of constraints along with the stakeholders' needs. And that can lead to discussions with the stakeholder of we can't build what you're asking for this budget. We need to make some changes, and then recommend those changes. System engineering seeks a best balance of functions and interaction within the system budget, schedule, technical, and other expectations and constraints. This is something that we got from one of our Saturn V engineers who passed away about 4 years ago, Bob Ryan. But Bob was something he would always say. He said, what you're trying to do as a system engineer is get the best balance of functions. And you want to do that within the budget, within the schedule, within the technical, any other expectations and constraints, which could be policy and law. You see the pestle icon here. And so that's really important to understand, that we're trying to balance everything out as opposed to seeking an optimum. And what does that mean, right? So look for that best balance. Systems engineering decisions are made under uncertainty, accounting for risk. I think we're all familiar with the importance of accounting for risk and the uncertainty that we have in our decision making because of that. Decision quality depends on knowledge of the system, enabling systems, and interoperating systems present in the decision-making process. Really important. The decision-making body, whether that's a board or a working group or a panel, needs to have all of the affected engineering disciplines represented, affected being whether they are executing some part of the design or whether they are impacted by the change. They all need to have a voice in the decision-making process. When you do that, you'll find that it's a pretty efficient decision-making forum. If you don't do that, you're always missing a voice in the decision. You will tend to make decisions that you will have to come back to later to fix any issues from the missing voices in the conversation. And so we don't want to have missing voices in our decisions. We want to have all the voices there at the table, all of the engineering disciplines, science disciplines, operations, maintenance, whatever constitutes your system, those need to be part of that process. And so we show that here in the graphic, we illustrate that. System engineering spans the entire system life cycle. This is here, it's important, and INCOSE said, hey, this is important when we looked at it. It's really important in NASA because NASA systems engineering processes end with development. NASA doesn't have processes during the operations life cycle, and that's not really correct. Systems engineering spans the entire system life cycle. Systems engineers are needed 10 years after you put the system into operation, just as much as they're needed during development to help during operations, to help with maintenance upgrades and obsolescence and requirements changes and new capabilities that are wanted to add. And there's a constant and maintaining that system understanding, which I think system models actually do quite well. This also has a series of sub-principles. And this is really focused, these sub-principles are focused on what is the role of a systems engineer. So a system engineer obtains an understanding of the system. System engineering defines the mission context or the system application of the system. The systems engineer models the system. Systems engineering designs and analyzes the system. We do that at the system level. There is design and analysis that is done at the system level to bring all the engineering pieces together. Systems engineering tests the system. Really important to have system level tests, or at least system level test objectives and lower level testing to make sure that you're understanding the system as it goes through test and learning about the system as it goes through test. Even subsystem tests can contribute to system understanding. Even component tests can at times. System engineering supports the production of the system. Really important to make sure that the design is actually being produced. And if they're making red line changes to drawings and other items in the production of the system, how is that affecting the system? Is that a fine change, or is that creating an interference or a different path, either low path or electrical path in the system that's problematic? So what is the impact to the system as you look at these things? So it's important to stay involved with that. System engineering supports operations, maintenance, and retirement, which are the phases that NASA doesn't have. That's really important for us as systems engineers to maintain. Principle 12, complex systems are engineered by complex organizations. If you have more than 2 people working in your organization, by definition, it's complex. And so when you're dealing with complex systems and you're dealing with organizations, especially if you have a large one, and it's thousands of people, it's a very complex organizational structure. It does affect the systems engineering. It does affect the solution of the system. And so you need to be aware of that and help to manage that from a systems engineering perspective. System engineering integrates engineering and scientific disciplines in an effective manner. That's our role, is to integrate the engineering knowledge and the scientific knowledge in the system to make sure that it's brought together well. And then systems engineering was responsible for managing the discipline interactions within the organization. So we're not trying to manage the disciplines. We're not trying to manage the organization. We're trying to make sure that disciplines that need to talk with each other are in fact talking with each other. Communication, really, really important. That's systems engineering responsibility, is to make sure that those interactions are happening. And when they're not, to work within the project management structure to help get those addressed. And so that's an important aspect, and this is a social aspect of systems engineering. And then the last principle, system engineering is based on a middle range set of theories. In other words, there's no single theory of systems engineering. It's a set of theories. And so we identified 4 systems engineering as a systems theory basis. Systems engineering also has a physical logical basis that is specific to the system. Different systems have different physical logical basis. Systems engineering has a mathematical basis. I mentioned category theory earlier. I think that is probably the basis for systems engineering, the math that really supports what we do. And then systems engineering has a sociological basis specific to the organization. So we've talked a lot about the subsystems. There are a set of hypotheses. Again, we're looking to conduct proofs on these. If a solution exists for a specific context, then there exists at least one ideal systems engineering solution for that specific context. Started proofs, but we haven't completed them, so that's still a hypothesis. System complexity is greater than or equal to the ideal system complexity necessary to fulfill all system outputs. It means there's a minimum complexity that you have to fulfill the system goals. If you have less complexity than that, you're not going to meet all of the system outputs that you need to have for that system. And then finally, key stakeholders' preferences can be represented mathematically, which goes back to value modeling. And that's still a hypothesis that's being actively researched out in the value modeling community. So let me go back to my charts real quick. I know we're almost out of time, and I'm cutting into the Q&A. It's out of the way. So we've walked through the principles using the principles document itself. So let me just flip through those. And just say that, we've put together the 15 systems, the 3 hypotheses, We've defined systems engineering principles guiding the engineering of systems, which provide guidance in the application of systems engineering processes and development operation of a system. I mentioned earlier the Insight magazine article, which is a good article if you like to read it. That's an earlier version than what's in the principles document itself. I mentioned CBOC, and that's the link there. And then there is a landing page, systems engineering principles landing page, which if you go to this, when you pull it up, you can download a copy of the principles document. But importantly, you can provide feedback to us. And so if you would like to do that, look at the landing page. You can give us comments on, hey, I got a principle or sub-principle that you should consider, or I recommend a change, or just a general comment. Identify specifically, it makes it easier for us to look at as an action team. And you can provide your contact information if you would like. You do not have to. And you can give us feedback, and we get those. This is a smart sheet, so we get these smart sheets, and as an action team, we'll be looking at them at the IW this year, to kind of let them collect up. So let me stop there. We've got about 10 minutes or so left, and let me just ask for questions.
Yes, thank you, Mike. Excellent overview and good timing too. So thank you for that. I have two questions in the chat. One is from Jan Johansson. It says on principle 7, mentioning changing stakeholder needs, but should it not also consider changing stakeholders?
Well, I think that's a great question. Yeah, so that's part of this. The stakeholders change, then the needs will also change, right? So we saw that as a subset of this. Yeah, that's a very good observation.
Yeah. And then Ahmed Khalaf, I think this is one of the later principles. His comment isn't seeking a balance of all aspects the same as seeking an optimal. So
that's a debated topic. We chose to say best balance here. If you go down and look at the hypothesis, that's what these hypotheses we're trying to get to. There's no clear definition of what optimal means in a systems engineering context. There's a lot of research on it, and I can tell you as a complex systems working group chair, when I've looked at it, complexity right now, when you look at how people define it, it's not really a definition, it's a description of something that they understand as complex. And so that understanding of that area and what does that mean to have an optimal is still developing. And so we decided not to do that because optimal means different things to different people, depending on what view they come from in complex systems understanding, depending on what view they come from in optimization theory. It means different things. So we thought best balance was the right and the more practical way to say that. And so that's why we chose best balance in principle 8. That's another good question.
Yeah, I sometimes use the phrase, if you try hard to optimize the subsystems, you will most likely sub-optimize the system. Very true.
Very, very true, right? And you need to optimize the system. When you talk about multidisciplinary design optimization, which is a very good method to use, that's what it's doing. It's looking at the system parameters and trying to hit a value function or an objective function, sorry, correctly, right? And what it's doing then is it's reducing the performance or sub-optimizing the performance of the subsystem. So, yeah.
Right. Then I don't see any other questions. I will open up the floor shortly, but I had the question myself actually, and that's how do you see the use of this document? Have you thought about that? How could an organization use this?
Oh yeah, yeah. We see a couple of uses, and we talk about it a little bit in the upfront material of the document, the preface and the introduction. But one is this helps guide the application of the processes. Right? When you look at these principles, you become aware of your organizational constructs, which means you might need to do something a little different. If you changed organizations, you'll find yourself maybe needing to do something different because of the way that the organizational culture is from your previous organization. I just recently started with Dynetics, and it's the culture is a little different than what I had at NASA. So as I'm looking at systems engineering, I'm looking at, well, how does this work in the Dynetics culture? And maybe there's some things in the NASA culture that didn't work that works well in Dynetics, and vice versa. And so applying the process, how you apply the processes is really, really important with the principles providing guidance to that. The other area is opening up research, right? Particularly Principle 15 and Principle 2, giving a mathematical basis pointing to physics and sociology. How do we get more definition in those areas? So we're hoping that the principles will lead to further research in the understanding of the basis of systems engineering. So those are a couple of purposes that we'd like to see, one in the practical world and one in the academic world.
Very good, thank you. Anybody else there who would like to unmute and ask a question? Well, if not, let me just finish off with tell you what's happening next. See if I can get okay. So can you see my screen now? Mike, can you just verify that the screen is visible?
Yes, it is.
Okay, thanks. All right, so this recording actually will be available through at our website. I will also make a link on, make a link to it from LinkedIn. So we'll be, probably if you've signed up for this through the event page, you will get the a little comment on where to find it. We will have some more upcoming webinars, so you can check those out here. And for those here in Sweden, we will have our face-to-face annual meeting in Gothenburg on the 9th November on the topic of electromobility. So with that, I'd like to thank Mike very, very much for your enlightening introduction to the systems engineering principles. I hope everybody will, join INCOSE if you're not a member, and download it, and maybe share some thoughts, and then fill out the review form for if there are something to contribute. So with that, I'd like to close this. I think there's a number of comments here that thank you, Mike, for a great presentation. So with that, I wish everybody a very good afternoon still, or a good day to you, Mike.
Well, thank you. Thank you very much for the opportunity.
Yeah, thank you.